Hello all, welcome to Electronic Circuit Laboratory. Today we'll discuss the experiment number 10. The title of the experiment is to design, build and test 3 op-amp instrumentation amplifier for typical application. The objective of these experiments are implementing the instrumentation amplifier using Wheatstone bridge and check the balance and imbalance condition. Calculate the output for changing the value of resistance, that is delta R. So first we see the Wheatstone bridge balance and imbalance condition, and then we can use a sensor with this arm, that is the fourth arm, by which we can get the change in resistance with this arm. If the physical parameter will get changed, the resistance will be changed. Basically we are using the PT100, that is a resistance temperature sensor, which is to be used over here, and output of the temperature sensor is nothing but the resistance. So if the temperature sensor connected in this arm, so if the temperature increases, the resistance also get increased. So depending on the increase in resistors, that is delta R, we need to calculate the output voltage, that is VAB. So VAB is calculated as VA minus VB. So if we consider this voltage VA and this voltage as an VB, so the difference of these two voltages is nothing but VAB voltage. And if you obtain this value of the VAB voltage, we can directly obtain the value of the resistance. So we can simplify this circuit using the basic network terminologies. So we implement the network like this. So here we can have the resistance, 4 resistors are connected over here, followed by the source, that is DC source VDC. All the values of the resistance are same. Means what? When the all resistance connected in each arm are equal, so in that case the difference of voltage VA minus VB is equal to 0, and that condition is called as a balance condition. So if you want to calculate the VA and VB, so we are having the formula for finding the VA and VB. So VA can be VDC upon R plus R into R, and similarly VB is equal to VDC upon R plus R into R. So if all the values are equal, so we can directly get the output voltage as equal to 0. So this is called a balance condition of the bridge. Now let's see how the unbalanced condition can be obtained and how we can get the formula for an unbalanced condition. So if you change the resistance of this arm, so we have the change in resistance, that is delta R. So I can take R plus delta R over here, and now I can find the value of VAB, that is VA minus VB. So I can just put the values over here with delta R resistor. If you solve this equation, we can get the voltage VAB is equal to VDC by 2 in bracket minus delta R twice R plus delta R. So the negative sign indicates that the point is at a higher potential than the point A. And if you take the voltage, that is VBA, so the B is at the high potential, so we can get the output as a VDC by 2 plus delta R upon twice R plus delta R. So if you know the value of delta R, R and VDC, we can directly find the VAB, or if you know the value of VAB, VDC and this resistance, so we can directly obtain the change in resistance. So this is what a balanced and unbalanced condition for a Wheatstone bridge, and the output of this bridge, this VAB is directly connected to the instrumentation amplifier. So we are using the instrumentation amplifier IC. So this is a practical setup or circuit diagram of a 3 op-amp circuit, but now in our case we are using the AD620AN IC, which is having inbuilt instrumentation amplifier. So directly we can connect this VA and VB to the terminal. So VA is connected to the inverting terminal and VB is connected to the non-inverting terminal, and this pin number 5 is connected to the ground as per the requirement. So for this circuit we are chosen, that is RA, RB and RC is equal to 1K and RT also 1K for balance condition. The biasing voltage, that is power supply given minus 12 volt plus 12 volt, and VDC is selected as an 5 volt. So let us see the procedure. So the first step, we need to build the circuit as in the figure. At balance condition, all the value of the resistors connected in the 4 arms is equal to 1 kilo ohm. Then we need to increase the resistance of the RT, this branch. So the RT resistance to be increased, so we increase it by some slight resistance by manually changing the value, and we can observe the value, voltage value at the output. so that we are going to change, and how that we going to amplify that we are going to change. So this is how we can implement this. So I have taken the 5 values of RT. So first is 1K, and then second 1.2, 1.5, 1.8 and 2.2. For all this value you need to calculate the theoretical value and also the practical values. So first find out the theoretical value using the equations, and then we can obtain the practical values with the simulation, and then we can cross check the results. So we'll directly shift to the simulation part. Yes, so this is the circuit that we have implemented in multisync. So now I just check it, the resistance once again and correct it to 1K. So this is what in balance condition we can say. So all the resistances are equal, so all the 4 arm of the Wheatstone bridge are equal. So we get the 0 voltage at the output, but practically it is not possible. So I can check it how much output voltage we are obtaining. You can see over here 293.78 microvolts, so very less amount of voltage is obtained at the output side, but theoretically we can get the output as 0. So now one by one we can change the resistance. So I just stop the simulation, can change the value of it. So it is 1.2. Again you can simulate it. Okay, so for 1.2 we can get the output voltage as 227.56 millivolt. So we can again change the value to 1.5. So the output voltage will be increased 1.5K. Again run the simulation. So you can see now we are having the 500.28 millivolt as an output. Then we will stop it, again change the value to 1.8. Yeah, the voltage is 714.56 millivolt. Now we change the value to 2.2K, which is our last reading. So we got the 937.77 millivolt at the output. So this is how the change in resistance with the Wheatstone bridge is applied to the instrumentation amplifier, and instrumentation amplifier will amplify that output and gives us a voltage value as per the requirement, and then these values can be again converted into digital form by ADC. So the instrumentation amplifier is very useful for amplifying the sensors output. So the sensor output is very less, which will again, I think in PT100 we do have the 25 millivolt or 26 millivolt per degree rise in temperature. If 1 degree rise in temperature is there, so the voltage will be rise by only 25 millivolts. So the small amount of voltage to be get addressed, and small amount of voltage will be get detected by the amplifier, and then it will be amplified, so by which we can convert it into digital form. So that's why instrumentation amplifier is used in various electronic system. So this is all about the instrumentation amplifier. Thank you.